Hello everyone, my name is David Chen, third year PhD in UIUC EC department advised by Professor Rakesh Kumar. Today I'll be presenting our work, CCPA, a concurrent content processing architecture for hardware firewalls. The core idea is simple. Today's hardware firewalls serialize packet processing unnecessarily, and by decoupling just the part that truly needs to be serialized, we can dramatically improve throughput on real-world traffic. Next generation firewalls are the frontline defense for data centers and large enterprises. The high-end NGFWs that you see here cost up to $2 million. They draw close to 10 kilowatts and they occupy 16 rack units. When you're paying that much cost per firewall box, you would want every DPC, which is every data processing card inside the firewall, to be doing useful work. Our work demonstrates that they are not well utilized in a lot of settings today. Here's how a modern hardware firewall is organized. Packets come in, they hit a network processing card for layer 2, layer 3 work. Then a load balancer distributes them to a pool of DPCs where the expensive operation happens, such as stateful inspection, signature matching, intrusion detection system, SSL decrypt, encrypt. Here, the critical constraint is that the DPC enforces per connection consistency, or PCC. Every DPC keeps its own local session table for modularity and also minimize traffic across the DPC boxes. And TPC treats out of order packets as congestion. So the load balancer is forced to pin every session to a single DPC for its entire lifetime. This is the main architectural assumption that we are going to challenge in this work. We observed that real-world network traces are massively heavy-tailed. Across every trace we examine, whether it's internet backbone captures, university data centers, DDoS traces, enterprise traces, a tiny fraction of flows carries more than half the total bytes traversed. In some traces, 0.0017% of flows account for 50% of the throughput. These are what the networking community calls elephant flows, and they don't play well with PCC in the firewall. Here's the problem in one single picture. An elephant flow gets pinned to one DPC, and that DPC saturates. The other DPCs are handling mice flows, which can consume their capacity. We confirmed this phenomenon on real-world hardware. When we're running iPerf3 through an OPNsense firewall, which is an open source software firewall, when we add more cores to the VM, it actually reduces the average utilization of the CPU because a single session cannot use them all. To quantify this systematically, we built a cycle-accurate event-driven simulator. The scheduler advances in 192nd quanta and walks data path graph in reverse topological order, so back pressure resolves in the same cycle. We validated against 5 commercial firewalls. You can see it here. The simulated NGFW bandwidth matches the report numbers within a few percent. Running real traces through the simulator on a 10 DPC firewall, we see that DPC utilization collapses on traces with few elephants. 30% on CIC, 65% on university data center. The specific load balancing algorithm barely matters. Whether you use round robin, least utilized, or symmetric hashing, and then this is because that PCC is forcing the imbalance, not necessarily the load balancing algorithm itself. And it gets worse as you scale. Adding DPCs doesn't help elephant flows. They are still pinned to a single DPC card. The gap between ideal throughput and achieved throughput grows with every DPC you introduce. Importantly, look at these curves for different blackping bandwidths. They are almost on top of each other. The bottleneck isn't backplane capacity, it's the PCC constraint itself. And here's the observation that drives a a lot of the design decision in this work. Packet processing has two main phases: stateful inspection, which touches shared session state and must be serialized, and content inspection, which includes signature matching, IDS, ML-based threat detection, SSL encrypt-decrypt, which takes the packet, the policy, and the session state, and essentially does pattern matching on it. Content inspection is stateless per packet. We measure the duration of stateful inspection and content inspection with open source kernels. Stateful inspection with MPF takes about 2 microseconds per packet. Content inspection in Suricata and NDPI takes hundreds of microseconds. Stateful inspection is less than 0.5% of the total work. We've been serializing 100% of the processing to protect 0.45% of it in today's firewall. To leverage this insight, we introduced CCPA. We introduced a new module called the State Checking Card, or SSC for short, that sits between the DPC pool and handles only stateful inspection. The SCC has 4 state processors, each with its own session table in local DDR5 memory. We expect it to be around 2.56 terabytes per state processor to match high-end NGFW session table size. A stateful load balancer pins sessions to the SPs, so each SP state is private and have no cross-chip locking and requires no cross-chip locking. Once stateful inspection completes, the SCC forwards the packet plus the updated session state to a DPC. We decided to go with round robin, so elephant flow packets now spray across all the DPCs. Content inspection is stateless given the forwarded state, so DPCs don't need to talk to each other anymore. We briefly considered letting DPCs do stateful inspection and then forwarding them to peer DPCs for content work. That needs an O2L crossbar and adds about 640 nanoseconds per hop on 7.5 microsecond port-to-port budget. However, our added dedicated SCC avoids this entirely. There is one issue with CCPA though. If a particular DPC finish in parallel, then packets can leave the DPC out of order, and the TPC will trigger retransmits after 3 out-of-order packets, as TCP view this as congestion. We solve this with a packet reorder buffer, PROB, at the SCC. A packet only egresses after the previous one has been cleared. The worst case PROB size stays under 16 megabytes even at 50 DPCs, which is very manageable. There's also 2 other efficiency wins by introducing the PROB. Now the DPCs only have to return the decision and not the packet, cutting the backplane bandwidth requirement by half. And for small numbers of rules, which we audited Suricata, and that shows it's around 5.4%, that these rules genuinely lead cross-packet sequential state, we can fall back to assuming PCC or per connection consistency. To show that CCPA is buildable, we prototyped the state processor in VITIS with VITIS high-level synthesis, and we mapped it to a Zinc 7000 FPGA. We were able to close timing at around 400 megahertz, and we only uses 5% of the LUTs, while sustaining a gigabit on minimum size packets. We exercised it with a random packet test bench and saw no drops and no reordering. Here's the main results. On high-end firewalls, which is around 10 to 50 DPCs at 50 gigabits per DPC, CCPA delivers an average of 4.29x throughput improvement across all traces, with peak gains of 11x on the university data center trace. The same trace benefits the most because it has the fewest concurrent elephant flows, which is exactly the case where the baseline suffers the most. We also envision that with a future optical backplane, the average benefits we can have goes up to 14.4x compared to traditional backplane. On mid-end firewalls, the gains are more modest, as expected, around 1.08x on average, because with only a few DPCs, the baseline architecture is already reasonably well utilized. The gains grow with scale, which is where the industry is heading, as network bandwidth demand keeps on increasing in every data center, in every enterprise gateway. Looking at the raw DPC utilization, we see up to 3.5x improvement on high-end configurations. And this comes in cheaply. Like the SCC plus the added DRAM adds about 3.35% cost and about 16% power on a high-end firewall, and which translates to a 4.29x throughput gain. Overall, to recap, today's hardware firewall over-serialized because they conflate stateful and content inspection. By separating the two and dedicating a state checking card to the sequential part, CCPA gets 4.29x on average, up to 14.4x with an optical backplane for only 3% extra cost. To our knowledge, this is the first work to identify and address this particular bottleneck in hardware firewall architecture. I'm happy to take any questions. Feel free to email me at the email below for any questions you may have. Thank you, everyone.